Alright, in this video I'm going to do a more thorough introduction to qualitative heat problems, or LOLs. Qualitative means like descriptions, not necessarily numerical. That would be quantitative. So in these we're basically going to be describing how heat is either entering a system or leaving a system using a couple pictures. So basically what these are going to look like is a graph before and a graph after, and the two graphs make the two L's, and then this circle in the middle is going to show our perspective. So that's where we get LOL from. It's the two graphs plus the circle in the middle. These E's stand for energy. And then we're going to go over what each of these three mean. Basically, it's thermal energy, phase energy, and chemical energy. We're going to be tracking that before and after to see what the differences are. So let's go through what these types of energy mean first. So ETH is thermal energy. That has to do with the temperature change. Okay, it's energy gained or lost during a temperature change. Really, that's referring to the molecules speeding up, because as the molecules get faster, that's your higher temperature. As they slow down, that's your colder temperature. So thermal energy is from the temperature change. EPH, that's phase energy. Energy that a substance has just by being in a certain phase. So you can think of this like potential energy as opposed to kinetic energy. Just by existing in a certain phase, matter has a certain amount of energy. For example, we talked about in class these hot packs, liquid hot packs. Okay, I don't know if you can see it, liquid there. Liquid hot pack. This feels like a regular room temperature liquid, but it really has a lot of energy in there just by being a liquid because the particles are moving quickly. Obviously, it has more energy in this than a solid of comparable mass, and you can see that because once you flick this little piece of metal in here, and it freezes into a solid, it's now giving off tons of heat. So really, the heat that you're feeling was that phase energy it had before. It had a lot more phase energy than a solid of the same size. So it's giving off that phase energy now, and you can feel that as a hot pack. ECH is chemical energy, and that's energy from a chemical change. So we're going to be tracking these three types of energy, and in fact you're going to see that it's really only the top two, and you'll see why, from before and after. So just a little more description here for EPH. We need to set kind of a standard, because basically on the L's, on the graphs, we're going to be putting little bars, like blocks, to show how much energy. Now the amount of blocks don't actually correlate with like how many joules of energy, because we're still qualitative. So for EPH, phase energy, that's energy just by being in a certain phase. For a solid, we're going to give it 1 bar, like this, just one little block. For liquid, 2, so that would be like the phase energy of a liquid. And for gas, we're going to skip 3 and go right to 4. And that's skipping 3 is kind of symbolic of the fact that when you go from a liquid to a gas, it's such a huge jump in energy. Solid to liquid is a relatively small jump. Liquid to gas is a huge jump. This is just like the whoosh lines. 1 for solid, 2 for liquid, 4 for gas. Okay, so that's EPH. For ETH, this has to do with the temperature. Now, 90% of the time, you're going to be dealing with water in this. Not every time, but for most of the time, you're going to be dealing with water. So we kind of set these temperature parameters around water. Now, you don't have to have this perfectly memorized. As long as you're consistent with yourself, that's the most important thing. But let's start in the middle here. When you have room temperature, which is like 20 to 25 degrees Celsius, let's call that 2 bars of thermal. Okay, so room temperature water, 2 bars. When you get hotter, when you heat that up, so it's around 100, so 70, 80, 90, 100, well now we're thinking 3 bars. Again, if you want to call it 2.5, that's fine as long as you're consistent with yourself. But this is kind of the baseline that we laid out. So room temp is 2 bars, hot is 3 bars, very hot, over 100 degrees Celsius is 4+ bars. What you need to remember is the boiling point of water is 100 degrees at regular pressure. Now, unless I throw any kind of mention of pressure in there, assume we're talking about regular pressure. So water is going to boil at 100. So if you want to get it over 100, you have made it into a gas. You have already boiled it, and now you have the water gas that's going to be heated up. Okay? So anytime you have 4 or more bars of thermal, we're already talking about a gaseous water. Okay? Now if we want to go cold, remember room temp is 2 bars. If we want to go colder than that, so anywhere around 0, so 0, 5, 10, 15 degrees, well, that's 1 bar. And below 0, very cold, below 0 is going to be a fraction of a bar. And again, since water is going to freeze at 0, so when it goes down to this, 1 bar, now it's going to start freezing. After it's done freezing, then it can drop below 0. You can never get water below 0 unless you do other things to it, like adjust the pressure or dissolve certain things in it, but that's something we'll get to. So this is like a baseline. If you're not exactly the way I am with this, it's fine as long as you're consistent with yourself. And finally, to chemical energy. Chemical energy is not going to be needed during this unit because temperature changes and phase changes are physical changes, not chemical changes. Basically, a physical change is any kind of change where you don't alter the chemical makeup of the substance, and a chemical change is when you do alter the chemical makeup of a substance. And by chemical makeup, I mean like how the atoms are actually, bonded together. So everyone knows water is H2O. So liquid water is H2O. Ice cubes are H2O. Water vapor, gaseous water, that's H2O as well. So by phase changing it, you're changing the way the molecules are interacting with each other, but you're not changing the actual molecule itself. It's still H2O. So therefore, ECH, we're going to be ignoring for this unit. We're probably going to return to ECH once we learn more about chemical changes. So let's start with an example of an LOL, and then I'll kind of talk through the process here. So in this example, a cup of hot coffee, 90 degrees Celsius, cools to room temperature, 25 degrees Celsius. Now, for these problems, we're going to assume that coffee is water. Soda is water. I mean, they are. It's not like coffee is a certain combination of elements or soda or anything like that. It's just water with stuff dissolved in it. So we're going to assume that coffee is water, boils at 100, freezes at 0. Same thing with things like soda or tea. It's all water. So in this case, we're going to now do our LOLs. So there's a first graph, there's a circle, and there's a second graph. Now let's start with the circle here. That's like your perspective of the problem. We're going to be tracking the heat going into or out of this coffee. So you put coffee in the middle here. As opposed to, in this case, could be like the room. Because really, if you think about it, if we kind of look ahead and guess what's going to happen here, you have coffee cooling down. That means it's going to be giving its heat out. So you could ask about the room, and the room would really be gaining heat. When you put super hot coffee on a table, that's giving off heat. So the room's technically taking in heat and getting hotter. So that's like your perspective. But for us, we're going to be looking at the coffee. And then what you want to do down here is write where you're starting from and where you're ending. And I want to see the temperatures and the phases. Now, if I don't give you a certain temperature, if I just tell you very hot coffee cools to room temp, you can make up your own, as long as it's within the ballpark of what it should be. Again, we're talking qualitative problems, so if you don't match my exact number of bars or my exact temperature, it's not that big a deal, as long as you show me heat going into or out of the system correctly. All right, so down here I want to start with my temperature and my phase. So it's 90 degrees Celsius, and it's going to be liquid. And you know that, not just because it says hot coffee, but because we're assuming it's water, and if you're at 90 degrees, you're in a liquid phase. And that's going to be turning into 25 degrees Celsius, liquid as well. Okay? You're not going to freeze it until it gets to 0 or anything like that. So that's our initial setup. So we're going to write ETH, EPH. Don't worry about ECH. No chemical change happening here. ETH, ECH, oh, not CH, pH. I don't know how that spade just got there, but ignore it. All right, so this is our setup, and now we're ready to start filling in our LOL. So I always start with phase first, even though I write thermal first. So starting with phase, we have a liquid. That's going to be 2 bars. Well, over here, we also have a liquid, and that's also going to be 2 bars. So it goes from 2 bars to 2 bars. So there's no change in the phase energy. It's still a liquid. It still has that phase energy, potential energy of being a liquid. Thermal is going to change, though. So 90 degrees Celsius, that's closest to 100. We're going to call that 3 bars. Okay? Over here, 25, that's room temp. I'm going to call that 2 bars. All right? So what you do now is you take the difference and you add it up. So I have 5 blocks over here, 4 blocks over here. The difference is 1. You're going to make that 1 block kind of hanging halfway in, halfway out of that circle. And now we're going to have to show, is it going into or out of the coffee? So the coffee started with 5, ended with 4. So therefore, did that energy leave the coffee or go into the coffee? Well, since the coffee started with 5 and ended with 4, it went out. So you draw an arrow going out like that. And that's showing that this 1 block is leaving the coffee. Then it's worth just pausing and checking. Does it make sense? When that coffee cooled down, did that heat leave it or come into it? Well, it definitely left it. And that's basically it now. So the first LOL is done here. Now, if you had gone for like 2.5 blocks over here and 2 over here, that's fine. You would show half a block going out. If you did 2 blocks over here for 90, you can't do 2 blocks over here though, because then you're not showing any kind of change. You can go 2 and 1.5, 2 and 1. I mean, that's fine. I would prefer everyone kind of matching what we do here, but again, this is qualitative. As long as you're showing the correct direction, that's all I really care about. Let's do another example. Cold glass of soda. Again, we're assuming soda is water. 5 degrees Celsius. Warms up to room temperature, 20 degrees Celsius. All right, so L, our perspective is the soda. So we're starting with 5 degrees Celsius, and that's going to be a liquid. And it's ending as 20 degrees Celsius, and that's going to be a liquid as well. So let's put our ETH, EPH, ETH, EPH, and let's start filling it in. So I always do phase first. We have a liquid over here, that's 2 bars. We have a liquid over here, that's 2 bars. No change in the phase. We start with 5 degrees Celsius. I'm going to call that 1 bar, because it's very close to 0, and I'm going to call room temperature 2. So it's going from 3 to 4. Difference is 1, and is that 1 block going into the soda or out? Well, the soda started with 3, it ended with 4, so therefore it must have absorbed that heat. So it's coming in. All right. Next example. You put a tray of water, 22 degrees Celsius, in the freezer, and it turns to ice, -8 degrees Celsius. All right, so this one's a little more complicated because, as you can see, we're going to be doing a phase change here. In order to go from 22 to -8, you're going to need a phase change. And for this, I just want to show what this would look like on a heating curve, or really a cooling curve in this case. So down, flat, down, flat, down. So if we're starting at 22 degrees Celsius, that's right about here. And we're ending at -8, which is right around here. So if you look at this, it's really dealing with 3 parts of the graph. In the first part here, you have the 22 degrees Celsius water cooling down to 0. Then you have the 0 degrees Celsius liquid freezing into solid, and the temperature is going to stay at 0. And then finally, you have that 0 degrees Celsius solid cooling down to -8. Notice that this is going to be a 3-step process. It's cooling down from 22, then it's freezing, then it's going to turn to -8. So it's not like it can just start freezing along the way. It has to go down to 0, then freeze, then drop down to -8. And each of those 3 steps is going to get its own LOL in this example. You might say, why are we taking the time to do all 3? Why can't you just do them all in one? And the main reason is, when we get to quantitative, which you probably should know by now, or at least have an introduction, those all have to be their own steps too. If I give you this problem and I give you a little bit more information and have you do it quantitatively, meaning mathematically, you're going to have to do it in 3 steps using 3 separate equations. So that's why we like to do the LOLs in 3 steps as well. So let's start. So we're starting with 22 degrees Celsius liquid and it's eventually going to turn to -8 degrees Celsius ice. So let me do the first LOL. All right. 22 degrees Celsius liquid, and that's going to turn down into 0 degrees Celsius liquid. Okay? Yes, it's going to eventually end up as a solid, but the first step is the liquid cooling down and remaining a liquid. It's not going to turn to a solid until it freezes, and that's going to be its own step. So the rule of thumb is you should either change the temperature or the phase in one LOL, never in 2, or never both. So let's put our perspective here. So we're dealing with water that's going to turn to ice. The best thing to put in the circle here is just H2O. Because it's really just, it's going to be H2O whether you call it water or ice. All right? ETH, EPH, ETH, EPH. Let's start filling it in. So 22 degrees Celsius, well, I always start with phase. So liquid is going to be 2 bars. Liquid's going to be 2 bars. So no change in phase just yet. 22 degrees Celsius, I'm going to call that 2 bars. That's pretty much room temp. 0, I'm going to call that 1 bar. So the H2O is going from 4 to 3, difference of 1. And is that 1 going in or out? Well, from 4 to 3, it must be going out. So that's the first one. Let's do the second. L, O, L, still talking about the H2O. ETH, EPH, ETH, EPH. So our water is now at 0 degrees Celsius liquid. And it's going to now turn into a solid. The temperature is not going to change, though. During a phase change, temperature is always constant, so we're going to remain at 0 degrees Celsius solid. Let's do our LOL here. So liquid is 2 bars for phase, and over here solid is 1 bar. So finally we're changing the phase. 0 degrees Celsius is 1 bar for over here, 0 degrees Celsius, 1 bar over here. Again, you either change the temperature or the phase. So you should always have one of these two being the same. All right, so from 3 to 2, the difference is 1, and that's going out because the water is losing energy. And on to our third one. Still talking about the H2O here. ETH, EPH, ETH, EPH. So the water has gone from 22 to 0, then it froze, and now we have 0 degrees Celsius solid. It's now in the solid state. It's ready to cool down, so it's going to end at negative 8 degrees Celsius solid. So starting with phase, we go from solid 1 block to solid 1 block. No change in the phase. 0 degrees Celsius, that's 1 block, and negative 8, that's cooler than 0. I'm going to give that half a block. So 2 to 1.5, that's half a block difference, and that half a block is going out. And that is it for the problem. So what we're showing is that when you put that water in the freezer, it's turning into ice and it's giving its heat away. So a couple things you want to do to check. First, all of your arrows should be going the same direction. So this is the first LOL, second LOL, third LOL. They should always be in the same direction. If you have out, in, out, you did something wrong. Second thing you want to check is, here's my first LOL. The one you do on the right here should be the same as the next one on the left, because really, that's your ending point, and then that's going to be the starting point of the next one. So this should be the same as that, which it is. This is the second one. This should be the same as that, which it is. So that's what you want to check. All right. So let's do one more example here. Hot gaseous water, 140 degrees Celsius, cools down to room temperature water. Now you might be saying, hold on, gaseous water, isn't that like, oxymoron? No. Water is really just H2O. I mean, normally we refer to water as liquid water, but water is just H2O. So that's going to be gaseous H2O, 140 Celsius, cools down to room temperature water. So if we just do a quick cooling curve here, 140 degrees Celsius, that's going to be up there, and room temp is going to be here. So as you can see, the first step is going to be cooling that gaseous water down. Then, once it's at 100, it's going to condense into a liquid, and then it's going to cool down again. So we're going to be doing 3 steps here. Cooling down the gas, then condensing it, then cooling down the liquid. So that's going to be 3 LOLs. Okay, so I'm going to put my H2O in the middle here. ETH, EPH, ETH, EPH. So we're starting with 140 degrees Celsius gas, and that's going to cool down until it starts to condense, which is 100 degrees Celsius, and we're going to still leave it as a gas. I don't want to show the cooling down and the condensing in the same step. So, EPH, 4 bars for gas. Gas, 4 bars as well. No change there. For thermal, I have very hot here. This is over 100. I'm going to give that 4 bars. 100, I'm going to call that 3 bars. So I go from 8 to 7. The difference is 1. And is that heat going into or out of the water? Well, it's going out. From 4 to 3, that water is losing energy. That's my first LOL. Second. So let's see where we left off here. 100 degrees Celsius gas. So the gas is now ready to condense. So the second one's going to be the condensation. So we're going to go from 100 degrees Celsius gas to liquid, and that liquid's going to stay at 100. During the phase change, temperature does not change. 100 degrees Celsius liquid. ETH, pH, ETH, EPH. So 4 bars for the gas. Liquid, 2 bars. So from 4 to 2. Thermal is going from 100 to 100, no change. So we're going to give it 3 bars over here and 3 bars over here. So I have 7 on the left, 5 on the right. Difference of 2. And are those 2 going in or out? Well, it's going from 7 to 5. Out. It's going out. Consistent with condensation being an exothermic phase change. In order to condense, that gas has to dump off its heat and turn into a liquid. Oops. All right. Last one. Still dealing with our H2O here. So our temperature is still 100, except now we're a liquid, and that's going to cool down to, what did I say? 25 degrees Celsius. And that's going to be a liquid. ETH, pH, ETH, EPH. So for thermal, we have 2 bars over here, 2 bars over here. Sorry, that was phase. Now for thermal, which is temperature, we have 3 bars for the 100, 2 bars for the room temperature, 25. Going from 5 to 4, the difference is 1. And let's see, since it's going from 5 to 4, it must be going out. And that's it. So let's check those 2 things again. First of all 3 of our arrows should be going in the same direction. Out, out, out. So we're good. Second, you want to check that the rightmost L should be the same as the left one on the next one. So this is my first one. So that should look the same as this, which it does. Here, this one should look the same as the next one. So 3 and 2, 3 and 2, good. So that's it. All right, next one. I would say you should pause the video here, try to work this one out, and then play again. So this is kind of a multi-step problem here. I'm saying an ice cube, -8, is placed in a glass of room temperature soda. And again, we treat soda as if it's water. Show LOLs for the ice cube and for the soda. So this is going to be like 2 separate problems. So think about how many the soda is going to get, how many the ice cube is going to get, and then do those separately. So when you pause, and then play when you're ready. All right, so in this case, we need to kind of come up with an ending point for it. So if you put an ice cube in soda, the soda's going to cool down. We all know that. And they're going to kind of meet in the middle. So the question is the soda going to cool down so much that it freezes by putting 1 ice cube in? Definitely not. So it's not going to reach 0. It's probably going to reach something like 15 or 20. In fact, 1 ice cube, it's probably going to be like from 25 to 20. So we're going to show this ending at about 20 degrees Celsius. So that's what the soda is going to do. The soda is going to go from 25 degrees Celsius liquid to 20 degrees Celsius liquid. And again, if you put 15 or even 10, I don't care. It's qualitative. You're still showing me the heat transfer going in the right direction. That's all I care about. So that's what I said for the soda. Now for the ice cube, well, it's starting as -8 degrees Celsius, and that's obviously going to be a solid. And if you put it in the soda, and the ice cube melts and the soda cools, obviously the ice cube is going to end up as the same exact thing. The ice cube is going to have to melt and then warm up to 20 degrees Celsius liquid as well. But since it started at -8 solid, this is going to be multi-step. So it's going to be -8 degrees Celsius solid, turning into 0 degrees Celsius solid. That's the warming up. Then it's going to melt, so 0 degrees Celsius solid, turning into 0 degrees Celsius liquid. And finally, now that it's liquid, it can warm up. 0 degrees Celsius liquid, warming up into 20 degrees Celsius liquid. So the soda is going to get 1 LOL. The ice cube is going to get 3. So I'm going to do the soda first. So soda can go in my perspective circle here. ETH, EPH, ETH, EPH. So we start with 25 degrees Celsius liquid. going into 20 degrees Celsius liquid. Phase, 2 bars on the left, 2 bars on the right. For thermal, 25 room temp, I'm going to give that 2 bars. Now, I would normally give 20 the same 2 bars, but I don't want to go 2 bars to 2 bars because that would really not show any kind of real change. I'm going to go with 1.5 here. You could go with 1, you can go with 1.5, just anything to show some kind of change. So that's my kind of best rendition, from 2 to 1.5. I know it's not perfect, but again, it's just qualitative. We don't really care exactly how it looks. We just want to see where the heat's going. So from 4 to 3.5 is half a bar, and that half a bar is going out because 4 to 3.5, so it's losing half a bar. It's going out. And then the question to ask yourself is, where is that energy going? Some of it's going to be going into the air, some's going to be going into the glass, but the majority of this heat going out is going into the ice cube in order to melt it. All right, so now let's do the ice cube. Ice cube. L-O-L. So I'm going to put H2O in the middle here. We're starting with our ice. It's going to end up as liquid water. ETH, EPH, ETH, EPH. So the ice cube starts as -8 degrees Celsius solid. The first thing it's going to do is warm up to 0 degrees Celsius solid. It's not going to start melting until it hits 0. We want to show that. All right, -8 Celsius solid. So solid is 1 block. Solid is 1 block for phase. For thermal, I'm going to give that half a block. I'm going to give this 1 block. So the difference is half a block. And is that going into the ice or out of the ice? Well, it's going in. Next, H2O again. ETH, EPH, ETH, EPH. All right, so now we have 0 degrees Celsius solid. It's now ready to melt. And it's going to turn into liquid, and that liquid's going to stay at 0 degrees Celsius because during a phase change, temperature does not change. So for phase, we have 1 over here, and liquid, we have 2 over there. All right, temperature's going to stay the same. 1 block on the left, 1 block on the right. So from 2 to 3, my difference is 1 block. And is that block going into or out of the ice? Well, it's going in. And finally, L, O, L, H2O, ETH, EPH, ETH, EPH. So we have 0 degrees Celsius liquid. It's now ready to warm up to 20 degrees Celsius liquid. Okay, so for liquid over here, 2 blocks of phase, 2 blocks of phase. Somehow I got a mystery spade put in again. I don't know what's going on. So 2 and 2. Thermal is going to change though. So started with 1 with 0, and for 20, normally I would do 2, but since, remember at the beginning of the problem, I said when it went from 25 to 20, it went from 2 to 1.5. I'm going to call this 1.5 just so I'm consistent with myself. So there's 1, and there's the half there. So from 3 to 3.5 is half a block, and that's going in as well. Okay? So during this problem, let me go all the way back. For the soda lost energy. And where did that energy go? Into the ice. And into the air a little bit, and into the cup a little bit, but mostly into the ice. And here's the ice cube. It absorbed energy. And where did it absorb this from? From the water. So the ice cube absorbed energy to warm up to 0. It absorbed more energy to melt into liquid water. And then it absorbed even more energy to warm up. And that's what happens when you put ice in soda. That's why we do it, because it's going to pull heat from that liquid to melt the ice. So that's it.